Buenas tardes.
Buenas tardes.
Saludos desde España.
Saludos desde Chile. Bueno, aprovechando este saludo, vamos a saludar, vamos a dar el buenos días o buenas tardes.
Good morning or good afternoon, depending on where you have joined us from in this second seminar. We are organizing here from Chile. First of all, I would like to inform you that this activity has simultaneous interpreting, for which you can select the language of your preference in an icon you will find in the taskbar below. Let me tell you that this seminar is recorded. It will be posted in the website of Copernicus Chile. Having said that, we would like to cordially welcome you to this second seminar out of a series of seminars we've been organizing called Natural Satellite Seminar in Chile and Latin America, Building Applications and Collaboration Networks. The first one was on climate change, and if you couldn't attend, you are kindly invited to visit the Copernicus Chile website, where all conferences and presentations are hosted. This seminar is called Natural Disaster. You can see the image behind us. And we would like to focus on discussing, knowing, and exchanging ideas on this phenomenon. This initiative is organized thanks to a collaboration funded by the Copernicus Framework Program between the Center for Mathematical Modeling from the University of Chile, on behalf of the Copernicus Reference Center Chile, and the Joint National Conservation Committee, JNCC, United Kingdom. To kick off this seminar, as I told you, it's called Natural Disaster. We're going to welcome Mr. Master Smith, Manager of Biodiversity, Ecosystem and Natural Capital at JNCC, and Mr. Florencio Trueras, Coordinator of the Copernicus Relay Center and the Mathematical Modeling Center Chile. Matt, the floor is yours.
Good morning.
I just recently saw. Here I am.
Good morning, everybody. Thank you very, very much for joining us for this second event. It's excellent to see it so well attended. As Carmen Gloria said, this is very much around building collaboration, strengthening the existing networks that are using both for using Earth observation for various applications. This week we'll be focusing on natural hazards, managing those risks, predicting those risks, and really exploring how the Copernicus data can be used to help us to manage these risks and to manage our landscapes in a more sustainable manner. Really looking forward to connecting with you over the week and hearing from what is a really excellent set of presentations. So yes, look forward to connecting to you more. I shall leave it there and I shall hand over to my colleague, Florencio. Thank you very much, Carmen Gloria. Thank you very much, everybody.
I'd like to welcome you on behalf of the Mathematical Modeling Center. It's a pleasure. We've been organizing this for some months, as Carmen Gloria was saying. I'm sorry, but the audio quality is low. You will find all the presentations in our website. We're very happy with the work you have submitted. I'd just like to welcome you. We hope to have a fruitful working week. Welcome. Thank you very much, Florencio and Matt. Now, I'm going to leave Mr. Juan Carlos Baez, who will be the chair of this session. Dr. Baez works in the National Center of Chile, is an expert professor at the University of Chile. His lines of research, among others, are seismology, geophysics, geodesy, seismotectonics. He has a prolific scientific production. Carlos, the floor is yours. Thank you very much, Camilarius. Good morning or good afternoon, everyone. I'm welcoming you to this second workshop of Copernicus satellite data in Latin America, particularly in the central subject, which are geological risks. So we have an interesting program with interesting panelists. I would like to remind you that this activity will have Dr. Montserrat with the first conference, then we'll have a Q&A session, 10 minutes. And then we'll continue with the presentation of on how the panel is consisted of. And once we finish that, we'll have a Q&A session. Then, let me introduce to you Oriol Montserrat. I don't know if he's over there, so he can share his screen. Here I am. Thank you, Oriol. I'd like to introduce Montserrat. He holds a PhD in aerospace science. He's currently a senior researcher at the head of remote sensing department at the Telecommunications Technology Center at Catalonia. His main fields of research include synthetic aperture radar, SAR, differential interferometry, SAR, and persistent scatter interferometry, PSI. During his research career, Oriol has participated in more than 60 publications where he is being the author and co-author, indexed journals, also some national and international projects. Among the latter, it's the H2020 project and a risk coast project. Oriol, I'll see if I can share my screen. Can you see the presentation? Okay, there you are. Okay, I'm not going to use the video so that we can avoid noise. Thank you very much for your introduction. First of all, I'd like to say that it's such a pity not to be there, because it's always more fun and more productive when you are there in person. But well, you know, these times make us be home, and let's hope to have a fruitful session in this mode today. I'm going to start with a presentation, and before going to the more technical part, I'd like to introduce the place I come from. I'm a senior researcher from the Telecommunications Technology Center of Catalonia, which is a new research institution starting as an initiative from the regional project in Spain. The center is based in Castelldefels, which is a municipality of Barcelona, close to here. I could say that we are practically in Barcelona. Among the research areas we work in the center, I would say that it covers different scopes of telecommunications, and then due to, I would say, geopolitical reasons, it also has a vision devoted to geomathematics, among which you will see the Department of Sumateria, the one developing all the activities you've heard of. just to give you some more idea about the context of this for this presentation, my idea is to provide you with an overview, obviously from our standpoint, on how Sentinel-1 images can be used for diverse aspects of geohazards, such as sensing, mapping, measurement, and monitoring of field movements. In this sense, particularly in this context of the presentation, sensing is to geographically locate areas being affected by movement. By mapping, I understand limiting the influence area. And when I talk about measurement, I mean to quantify the movement, how much movement you'll see there. In this case, refer to its evolution in the past to date. And by monitoring, we understand. So today, tracking or follow-up from what's happening there. Okay, before observing the applications, I'd like to give a brief information to what SAR means in the lab movements. So by SAR, we understand it's a system formed by a sensor, a radar, in a platform that transports it. In the case of today, we're talking about satellite platforms, and in the end, the function is that the radar starts to emit and receiving responses from the lighted image throughout its journey in the orbit. So in the end, what we can obtain? We can obtain a sample, a two-dimensional thing from the field where images are formed by pixels, and each of these pixels represents a certain field area. And for each of these pixels, we have two components or two types of different informations. On one hand, we have the phase, which in the end gives us information about the distance between the satellite and the field area. And then we have the amplitude for each pixel, providing us information on how they react or how they respond when it comes to the lighted image. Then, to give you an example, here you have an example of an image of amplitude, SAR, SAR. In this case, we're in the airport zone, Barcelona, and the amplitude, from an illustrative point of view, will be, to me, has always been like the nexus between the world of normal or regular human being, which is the optical world, and the radar, which is the weird world, because in the end, it allows us to better interpret the radar images, which are complex themselves, and besides, this allows us to use classical techniques of teledetection and the optical in the scope of the radar. It's much more intuitive. On the other hand, we have the phase. The phase itself is a strange thing from the data interpretation point of view, because the phase of an image by itself does not make sense, just noise. So in order to interpret it in one way, what we need is using comparison, phases comparison between different images. And then we use phases of at least two images to obtain information. And how do we do that? Finally, we have an illustration to simplify the concept, but we have a point here. The satellite goes through it. It acquires or obtains the first image, and based on that image, what we derive from it is the phase in that point, and as you can see, is related due to the distance between the object and the satellite, the point and the satellite. So you can imagine that the point is being affected by movement or not, and after a time, you have the satellite, then we can obtain the second phase, which is related to the new distance between the satellite and the point. So if we made a difference in these phases, which is what we call the interferogram, finally, what we can see that this interferogram can be broken down in two components. In one component that will be the phase due to the trajectory of the signal between the point and the satellite, plus a component due to the displacement, an increase due to that trajectory. So given the point from what the satellite obtains and the measurement is exactly the same, this component you can see here is automatically aligned. So what we have here is that our interferogram is giving us information only about the movement of the point. However, 99% of the cases, I would say that this never happens, and then what we have in the here is that our interferogram has a component that comes from the movement, plus a component that we call topography component that has to do with the geometry of what was acquired, the satellite position in the two moments of the acquisition and the distance regarding the point. All right. One thing is that if we know the topography of the terrain of the land, since we have all the information of the interferometry of the acquisition, we can take a field digital model similar to the topographic component. And in the end, what we can do is to get rid of them from our interferogram by obtaining a differential interferogram. And in the end, ideally, if we take this topography, what we have is our movement, which is what we can see here. Then this would be the ideal and fantastic world. And if it were like that, there will be anything else to talk about, because the problem is simplified now, and then we just can take the face. But unfortunately, almost all the cases it's not like this, and our differential interferogram, apart from the movement component, which is the one we want, it has diverse secondary components, being an obstacle when we want to estimate the moment. The components are the atmospheric component, that's the name it has, and that's due to the different conditions, environmental conditions, in the means through the probe trajectory to and from the satellite. And when we have something called topographic residues, which in the end, they are due to the fact that in this step, I mentioned previously, we use a model, and as any model, it is imperfect, and it does not faithfully represent the field surface. Even when we remove a lot of the topography, we always have, as a part of the face, being affected by mistakes of this digital model of the field. And finally, we have what we call noise. And although it might be a noise contribution from the sensor, and there's also an important contribution due to the fact that between the different acquisitions, the object or the portion of field being lighted in pixels, or the contribution by pixels, changes their physical properties. Then, in the final phase of the final value of measurement we have, results in an effect, and finally, this is noise. Then what happens here, we can find two types of cases. At some points, it might be that the three components compared to the movement component, which is the one we want to measure, then based on a differential interferogram or by using some special interferograms, we are capable of obtaining the information of on movements. In this case, we generally talk about interferometric application. When this does not happen, when we really need to use a bunch of images, we need to use models to estimate the information. We need also some other models for the atmosphere and so on, and statistic tools. Then at the end, we talk about applications of diesel, advanced diesel, or then I'll tell you, or I will teach you some examples. I'll show you some examples for the applications. Then in this equation, in this technique, what has Sentinel-1 contributed with? It was launched in 2014. Back then, we had a lot of sensors in the space. There's information here of the ones I know, and some of them planned for the near future. But I would say that currently we have around 15 operative constellations, star constellations. Each of it has their acquisition policies and distribution policies. Each one presents different resolutions on Earth. But in the end, the message here is that SAR, S-A-R, is a consolidated tool with several applications, and particularly for geohazards, it has an enormous potential. Then we focused on Sentinel, the constellation, the Sentinel constellation comes from the European proposal in the stake band, around 5.5 centimeters. Then we have in VSAT some data in between with images. And then we had Sentinel-1, which was like the consolidation of the European Spatial Agency and with some properties I'll tell you about. So finally, it's an interferometric sensor. That means that we can use the amplitude and the phase. The resolution is relatively good. It changed a little. No, it changed a lot regarding the previous ones, because in the end, it improves the resolution. That from the point of view of interferometry is the important one. And finally, in the incidence angle, it depends on from where you look, the image you will get. Sometimes can be better than others. But what was interesting from the point of view of Sentinel, not the sensor itself, which is also important, but the acquisition policy and distribution policy, as well as the orbital design. On one hand, a satellite with a type of 6 day was planned, and the acquisition is between 6 or 24 days, depending on the place in the world. In Europe, they guarantee 6 days. What's most important about it is that it is not a potential revisit, but it's a real, an actual revisit. It is acquired every 6 days in all Europe and around the whole world between 12 and 24 days. You had an issue of the world every 6 or 12 days, and there's a big change. It used to be lower than that measurement. The second important thing here, in my opinion, from the deformation of the field standpoint, is that the satellite moves in an orbit with 150 meters of radio, and that gives us, little sensitivity to the topography. There's the smaller little sensitivity here in this acquisition policies and this orbital tube and the revisit. What it does is to mitigate some noise by broaden the potentialities of coverage due to the phase. And on the other hand, the visit time has been beneficial for the atmospheric component, and in some cases, interferometry was being used to measure atmosphere properties. Some work has been published on that, and the orbital tube, what it does, the base, the difference, talking about the distance between the satellite and the acquisitions, to take it in the optical port to give you the stereoscopic capability, sensitivity for the field topography. The shorter distance, the lower, less sensitive we are to topography, and therefore less sensitive to the mistakes we make when we subtract that. In a few words, it mitigates greatly the mistakes of topography. If we add to this free data with no type of restriction of use, even to the business, in the end, Sentinel-1 has caused a revolution in development and the application of the techniques used. In short, before Sentinel, when we talk about SAR interferometry, we were talking about a measurement tool, it was depending on the images you have, whether you had images or not. And now we talk about monitoring tool. So today you have the guarantee that at any place of the world you can have data from the past, so you can measure what happens, and at the same time you can plan, you can monitor. The second characteristic, important one, or the second important achievement, in my opinion, is that before Sentinel, we used to talk about a tool that was mainly important in the scientific area, and today it is also important in the scientific area where the relevant continues to be important, but being expanding when it comes to their uses such as civil protection, urbanistic mitigation, mining, where it has a lot of applications, and more frequently in civil engineering. We'll see some examples of the things we are doing, and then to give some context in what the state of art is like. I'll talk about the amplitude applications. I believe that day by day has a great potential, particularly because we have a big bunch of images. Every 6 days, we have a new image of our places of interest, and in the end, it allows us to think of amplitude as a monitoring tool for displacement. And then for sensing or detection, which is another very important aspect of SAR. One thing I haven't said, and it gives value to it as well, is unlike the optical, it is easier to interpret, and SAR guarantees to have acquisitions regardless of what meteorology is. We are not interested in clouds, so to speak. So it's perfect in the optical, and particularly in emergency activities. So let me tell you, an scope we are working today. Papers are more and more on this area, and it's about the use of SAR and artificial intelligence for sensing and mapping of landslides. So the context is always maps, big maps, for the emergency teams to plan equations in natural disasters such as earthquakes or great events of rain and some others. This is something that no long ago was limited to optical images with all the limitations they had. Nowadays, it's being improved when it comes to the use of SAR for this type of applications. Let me give you an example of applications. This is a Hokkaido work being recently posted. The idea was to compare the SAR with the results obtained through the optical, and the idea was to use the SAR along the networks. I don't know the name in Spanish. Neuronal networks. So what was the result? Here you have the result obtained through optical. All these displacements found after the earthquake in Hokkaido. And here you have the result obtained with SAR. You cannot see well here. You cannot perfectly compare it. In the end, the result, well, the conclusion is that results can be compared with the same level of accuracy when it comes to sensing or detection. And as I was telling, this is a promising result because what it results in is more possibilities for the use of data after an event. The limitations we usually have is the revisit, and the idea of using various sensors for the same objective allows us to reduce greatly what happens after an earthquake or another type of event.
Well, here, I don't know if the presentations are going to be available, but here we have some references of studies we have done, lately. This is another interesting application of width, which is getting more important, which is not new from the technical viewpoint. But since we have more images now, we can do more. This is a follow-up of following dots through time. This technique, as I said, is being used with different methods, but in the end, it is basically about finding homologous points in consecutive images. By these homologous points, we understand points which represent the same element on the ground and the displacement of it. Different from interferometry, we're talking about asymmetric or metric imprecisions, but it has shown as a useful tool for different types of movements which are, for example, the ones which affect the glaciers and also the ones that affect landslides, which are rather fast, usually slow, but also some others which are fast. An example over here. This is in Chile. In this case, this is Campo de Hielo Sur. This is a map of the medium speed between 2014 and 2021 in these glaciers in Campo de Hielo Sur. We're talking about 500 kilometers times 100 kilometers. It is done with width. So the goal it is to analyze the cinematics of different parts of Campo de Hielo Sur and trying to see the variations and explaining them in the context where they are at. Here we have some more details. In this case, we have a glacier strip. This is the glacier that I have shown before. And here we have different measuring points. And in each of them, we have some different arrows indicating the direction of the movement and their scale according to the magnitude in terms of speed. We're talking about meters per day. For each of these arrows, we also have its variation through time. So here we see how they vary through time, the speed of this point. Here we can see stational periodicity, which is quite clear. But at the very end, the message is here that with width, we can get massive measurements in all of the Campo de Hielo Sur zone, which is a regional zone. And maybe, not now, but maybe in 20 more years, with all of the accumulations of data, we're going to extract important values related to climate change. So part of this work has been published not long ago, and now we're working in doing the interpretation of the results. We talked about width, and width, it is an important component nowadays for detection and also for monitoring. So now we're going to concentrate in the phase. As I said before, this phase can be divided into two applications: interferometric applications and also the DINSAR or MTINSAR. Let's talk about some applications which are going to be important, especially for using Sentinel. After that, more than going into details to what can be done, I will speak of a project which is being developed in Europe, funded by Copernicus, and also funded by Environmental Agency of Europe, which is called GREMS and Service, and it wants to give a map of deformations all over Europe and also about landslides in Europe. Let's talk about some interferometric applications. Something that Sentinel has contributed with, it is reinforcing an application, classical application of interferometry. The first map, the first interferogram was this application. This is the ecosystem interferogram. This is an image after and before an earthquake. We do an interferogram and we see how the surface has changed due to the interferogram. So besides being something quite beautiful, I really think it is beautiful. This represents the movement that has happened. And in order to interpret it, between each blue of these arcs, between blue and blue, we have 2.5 centimeters of displacement. So this tool, besides being beautiful, it is useful for geophysics in order to obtain a better interpretation of the earthquake that has occurred. Besides this application, which is classical, from the Sentinel viewpoint, which has allowed us to apply, it can be always applied in every seismic higher than 4.5. It is applicable everywhere in the world because we have images. We also have them in ascending and descending, so it also improves the interpretation. But besides that, we can also go to some applications which are much more basic of the interferometry, such as, once again, the detection of active geoforms. In that way, we work towards inventorying, which is also an important activity, knowing the things that are moving or not. That is quite important. And having them mapped, it is also relevant. So in that sense, what we do, and what I will show you, is that we have been working with this type of data, which are interferograms, In this case, we are in Los Andes. I don't know if this is Aconcagua Mount, but it is Los Andes. And what we did was, for all of the interferograms, we drew all of these things that you can see here with different colors. So in the end, by putting all of these geoforms over here that we detected with the changes in colors, which I mean means something that's making a change in the phase, and with interpretation, with inventories of glaciers and glaciers of rocks, we created an inventory of glaciers of rock which are active. So here we have the result of that work, a work that we did at that time. And then in the end, the idea was to say, with these interferograms that Sentinel is showing, with after 6 days with 6, we have interferograms which contain plenty of information. So we can use it for many different things. And it is true that in this case, we needed an expert user delimiting and interpreting these interferograms. Up to now, we're working, not only my group, but many other groups, in getting this in an automatic fashion. There are plenty of articles, I mean, not plenty of, but a few articles which are on this, about this, but they are limiting their studies to some limited situations, volcanoes or subsidence, for instance. So anyways, it is something that is being worked. The same principle can also be applied for landslide. So in this case, we're showing an update of an inventory over a zone in Italy, in Malaysia. This was one of the first things that we did with Sentinel. And the idea here was to, instead of inventorying glaciers of rock, we inventored landslides, active landslides after a rain event. We're not talking about collapses. We're only talking about zones which got activated and started to move due to the weight of the water. So in this concrete case, we could update an existing inventory, detecting new landslides, movements, improving the mapping that they had, and confirming some others that we had there in the inventory. So the reference is also over here. Once again, as I said in the former example, everything related to automatic detection in interferograms, it is a work of line which is quite, I mean, many works in the world are working with it. And finally, a topic which I believe you are quite developed, it is the application of interferometry, classical one, for the early volcanic detection. An example, in Spain, we implemented it. It was implemented in the National Geographic Institute, monitoring volcanoes in Spain. There are not so many, but lately they're quite active. And in this sense, the interferometry was an important input for understanding, better understanding what was happening, and in order to trigger the evacuation alert before the whole event, volcanic event started there at La Palma. In Chile, it's been used for many years, and the only handicap that you have over there is that many of your volcanoes, active volcanoes, have snow, and snow, it is not friendly with the phase. It provokes or creates many different effects and some noise amongst them. So it is not just like in the Canaries, it is much more complex and it's much more difficult to work. Well, in order to finish then, we're going to the monitoring applications. Do I still have time? 2 more minutes. As I said, the European Ground Motion, it is a service that it is being implemented nowadays. So CTCT, it is the expert committee defining the requirements, technical requirements, quality control, and follow-up of the validation. The product, it is mainly aimed to landslides and its possible effect in structures and urban structures. It is going to offer a map at an European level, and it should start the first semester of 2022. There is a planning of updating, which should be once a year. In this case, we use INSAR multitemporal. Different groups are going to be working with the development of the material which is being processed. And in a few words, what we're trying to do, it is exploiting the huge number of data that we have in order to obtain a better point selections, to have a better coverage and have a better mitigation of the elements such as atmosphere. So what we expect it is to have a map similar to this one, where we have the speed of the displacement. Over here, we have the Barcelona zone with many different subsidence phenomena. And for each of the points, we're going to have its evolution through time. So what products are we going to offer with this ground motion service? First of all, we have the basic product, which is level 2A, which is going to be a product which is going to be independent for each of element, for each acquisition of spatial acquisition from Sentinel. It is going to be delivered individually. It is going to be delivered in line of sight. We're going to measure the movements on the line from the satellite up until the ground. And we're going to process, it's going to be processed at maximum resolution offered by Sentinel. So the only handicap here, it is that the availability of measures is going to depend on the coverage and spatial coverage. And this will depend on the type of coverage on the ground. In Chile, if you try to do or use this service, well, in Chile, you will have a north, which is quite dense, and a southern part, which is so difficult from the coverage viewpoint. But, well, everything can be improved. Then later, there's a second product, which is called calibration. And what it tries to do, it is to create a mosaic of all of the different frames which have been processed. And it's going to do it calibrating the different references with GNSS. So over here, the main handicap that we're going to have, it is that we have a bad distribution in GNSS in Europe. And therefore, there will be zones which are going to be much more robust than others. But this is something to be confirmed and ratified and to still be worked. The product is going to be worked in line of sight and maximum resolution is going to be offered. Here's one example, calibrated, ascending and descending over the same zone. So what we get with this is that products can be compared. Green means the same here and over here in the two images. And finally, we're going to have a third level, ortho product, which is a lower resolution because we need to reduce the resolution to obtain it. And what it gives us is, instead of having two lines of satellites going from north to south and south to north, we want to obtain the displacement of two components, east and west, and the vertical one. We reduce resolution, but we create a product which is much more interpretable for most of the people. It's quite much simpler. So once again, over here, the coverage will depend on the availability of points in both trajectories. Here we have an example of this decomposition in vertical and horizontal. If this is a zone, as you can see, has some subsidence, vertical movements, and over here, it has no horizontal movements. And finally, the question is, what for do we want? What is it for? The truth being said, the answer is quite clear, but sometimes it is worth it to say it anyways. To summarize, we want to know better our territory. This is quite important. For instance, for activities such as prevention, detecting some threats for the places where we live at or we use, for the planning, because as has been shown here in Europe, we have plenty of cases, avoiding building in areas with some difficulties. It reduces cost, but it also reduces some of the costs, such as that people are going to miss their houses and so on. And also, it is a characterization. It's quite important because sometimes, knowing that a place is moving is important, but also knowing why they move it is important. Which are the triggering factors, which is the influence, scope, and then later planning some mitigation alternatives. It is also important. And this, of course, contributes for all of these elements. And finally, it is good for alerts, early alerts, detecting zones which are moving. It is important in order to know what's happening there. And over here, I wrote to be demonstrated. It is maybe in the future, as we accumulate more information and as we accumulate more knowledge, well, we'll be able to predict. So far, the database, it is still there and it's been worked. So finally, it is important to work in a multidisciplinary fashion. Besides us, I mean, we're playing with data, we're processing data. We like to do and use our methods, but we also need geologists making sense of our lives. Let's say it that way, right? We also need engineers to be picky with situations and which are forcing us to be better in the transmission of the results in a clear way, which is not ambiguous. And finally, we need, of course, to create the effort of many different people. So that's all. Thank you very much for your time. And I'm really sorry for, having exceeded my time. Thank you. Thank you very much for this excellent presentation. So we have a couple of questions. Felipe Ugalde is asking, do you use any algorithm of cross-correlation to estimate the displacement of the Campo de Hielo Sur with images of width? Yes, in Campo de Hielo Sur, we are using cross-correlation, which is incoherent. That's the way we call it, which is using only the width, the amplitude as a parameter. Erling Johnson is asking, we have a volcano with glaciers and snow surrounding it. So therefore, there's always a loss of coherence. So how can we verify if this activity with a typical INSAR width, or is there any other method which is better than that one? That's what I told you. In the case of La Palma, everything is beautiful from the viewpoint of the LINSAR because we have a rock which is quite coherent. And the only thing we need to deal with it is the atmosphere. It gives some issues anyways. But in the case you're telling me where you have snow, every single type of snow which is not dry, snow which has suffered a physical change, it has got some water, for instance, it supposes a total loss of coherence. And if you add a glacier, in that sense, a glacier also has some movements. So therefore, I would tell you that it is a difficult case. I wouldn't use INSAR as a tool of early alert in order to try to see something there, because I would say that I would try to find another technique. Anyways, there must be an expert in volcanoes that can give a further opinion and with a higher background in the use of INSAR in volcanoes. So also some other colleagues may contribute in order to answer that question. One last question from Francisco Delgado about the mapping of speeds coming from the amplitude of Sentinel-1. It is not available in the article of Mateis et al. 2021. So Francisco is asking, what is the reference, the correct reference? The reference, in order to see those results, it is under development. In the article of Mateis, we describe the method, and it's spread with optical images. So the method that it's used, which is cross-correlation, it is cross-correlation, but accelerated by a method of the medicine, because in this case, we tested with optical. So therefore, there are some results about one part of Campo de Hielo Sur, of a glacier, I forgot the name of the glacier. And the idea there it is that we are producing the article, which is going to show the whole Campo de Hielo Sur, and we're also working over the interpretation of it. And also we're cross-validating the results between optical and radar. We're also we will try to get some type of interpretation from it. Thank you very much, Aurel. A last question from Mirao. Are there in Chile some zones where we have many or landslides, but we have the problem of there is no much more reflection to do the interferometry? And I've seen that you have some articles reading about the usage of passive reflectors and active ones. So how much does it improve the estimations of the movement of this ground when using these type of reflectors? Over here, I will answer in two sections. The first one, the goal of the reflectors, it is having some points in the ground, whether they are passive or active. So what it contributes with, it is going to the classical method. With a reflector, in that point, you're going to have some response to radar, right? So therefore, you'll be able to derive information about that point. Usually, if the zone you're analyzing has no points, with one reflector is not enough. You need to install many. Afterwards, if you get the difference between active and passive ones, here you go into logistics. The active one, it is smaller, it is not so visible, and that is sometimes important, and it could even be a cover or hidden, because in the end, vandalism is always there. And sometimes you install something there, and someone, I don't know, it has happened that they have destroyed it, and they have created a grill. So the smaller, the better. As a disadvantage of the actives against passive ones, an active one needs to be fed. There are some solutions, for instance, solar panels, but if there's no sunlight, the active one does not make any sense unless you have some feeding source. But both contribute with the same from the measurement. They guarantee having measurements on the ground with interferometry. Perfect, Oren. Thank you very much for your excellent work and also for the answers. There are still some questions, but I imagine the participants will be able to send you an email with those questions. But because of time constraints, we're going to close this conference and we're going to continue with the panel. So thank you very much. So now, I want to introduce the panel that we're going to have, monitoring the Earth. And we have 3 panelists. So please turn on your cameras. Mr. Arpala, Paula Oleancina, and Francisco Delgado. We're going to start in the same sequence. At the very end of the presentations of each of you, we're going to have a Q&A session. So we're going to start with Jorge Alpala. Jorge, he's a civil engineer. You can share your screen, Jorge. He's a specialist in GIS, and he's a master in geomatics. He works at the Papayan Volcanological Observatory of the Colombian National Seismological Center. He's going to present the applications of satellite images Sentinel-1 for the monitoring of deformative processes in Colombian volcanoes. Good morning. Can you hear me? Yes, we can. Well then, so it is good morning. First of all, I want to thank you all. Thank you for the invitation. I want to thank people here, all of the participants in Zoom and different social networks. Thank you very much for the invitation. And today, I'm going to share a lecture which is called Application of Satellite Images Sentinel-1 for the monitoring and deformative processes in volcanoes here in Colombia. As it was said in the introduction, I am Jorge Alpala. I work at the Colombian National Seismological Center. We work in the monitoring of active volcanoes. And we use the technology, satellite technology, especially Sentinel-1, for the monitoring of a process, deformative process on volcanoes.
An introduction. Colombia is based in a tectonic area, a very active one. Same as other South American countries, we are here in a convergent zone here of 2 main plates, which is the Nazca plate and the South American plate, which gives this phenomenon subduction. This phenomenon has caused several volcanoes from the north to south and the rest of the South America volcanoes. This phenomenon is one of the triggerings of earthquake we have had in all the Pacific coast. You may remember ones from the south of Chile until Colombia. Colombian territory, generally speaking, has four hazards, well-identified volcanic hazard, which is the first one. We have a great antecessor, which is the Nevado del Ruiz volcano from 1985. We well know generated around 25,000 fatalities. At that time, we didn't have in Colombia an official entity for monitoring volcanoes, and neither was it done with the accuracy was done today. One other volcano representative is the Galeras volcano in the south of Colombia, which has been pretty active between 1984 and 2010, with some eruptions, periodical eruptions. It presents a recurring seismic activity. This Huila volcano is in the central area of Colombia in 20,000 and at least at 24 hours. We have an increase in the activity, and it had its first eruption in 27, 8, and 9. There was some periodical eruptions whose purpose ended in 2011 and 2012 with the destruction of a lava domo in a surface of 90 million cubic meters. One more thing we have, one hazard here, we have flood hazards. According to a study, 28% of the territory is in high threat or hazard. Another phenomenon close to the tropical zone. Colombia is a country where we have several rainy seasons and high rainy seasons. Then we have hazard due to landslides, and 8% of the territory is found under a high hazard, seismic hazard. We have in our territory in the past has been affected by seismic events of big magnitude, such as the Tumaco seismic in 1906, about 8.8 magnitude. Then Tumaco 1958, 7.8. The Popayances earthquake, that's where I live in 1983 with 5.5. Paz earthquake 1984, magnitude 6.4. Eje Cafetero earthquake 1989, magnitude 6.2. All those earthquakes have generated a series of destruction in the territory, and they have generated losses, both material and human losses. Facing all these hazards in the territory, the national government designed the Colombian Service as an entity for the monitoring of these geological hazards. The monitoring has been done from different science fields: seismology, geology, geophysics, geochemical, and geodesy. In the particular case today, we'll refer to geodesy, and we'll refer to a particular phenomenon that's monitored under geodesy, known as volcanic deformation. The volcanic deformation is a physical phenomenon experienced by the crest of a volcano during, before an eruptive process, or it also happens when there is an earthquake of a great energetic contribution. We have two these figures representing the surface of a volcano. A volcano is deformed since deep levels, this magma contribution that is loaded of a new volume, different temperatures, which make the volcanic walls to be broadened. Sponge, that's called as inflation, known as inflation. Once the eruption occurs, those walls tend to distress, relax. That's called deflation. That can be produced by eruptive events, also seismic events occurring close volcanic buildings. We'll see that in some more examples. Volcanic deformation traditionally is monitored with techniques such as nivelation, dry inclinometry, electronic inclinometry, electronic measurement, remote, GNSS, permanent GNSS, and star interferometry. In Colombia, as it was mentioned before, interferometry is a relatively new technique to us. And why is that? Because we didn't have the capability to acquire commercial images from the software, from the commercial software, which is pretty costly. Our organization, government organization, in order to acquire that image, needs to go through a tendering process, and it takes a long time. we know this phenomenon can occur in a couple of hours or during some days, and we need to give some response to the authorities. So until 2014, basically in Colombia, we didn't do interferometry. There's some studies of interferometry, but they are very specific cases by private entities. As a government entity, we started to do interferometry after 2014, which is the year when we have the Sentinel constellation, that with the availability of free images. I have, well, interferometry has been already explained. So interferometry is a sensing technique measuring the interference pattern of the electromagnetic waves of those star images. These images are both master and slave images. The master image is the image before the event when we analyze to calculate, and the slave image is the image we have after the event. These images must comply with some conditions that might be acquired, preferably from the same point of view, from the same point in the space, with similar observation angles and in different times. The interferometry term makes reference to interference and measurement. Here, we basically have a satellite emitting some electromagnetic waves on the Earth's surface, and that it depends on the state of the surface, because it will take time in SAR. When the deformation occurs, that surface changes its form. Then that light will take longer or shorter. And with interferometry, we see a difference in phase. And why is that? Because that surface moved, then that will take us more time. In terms of methodology, the methodology, you can see it in different papers. This is a way to describe it generally. We have two images, master image and slave images. Ideally, these images should have the same direction, up or down, you see, bottom up or bottom down. And then we do is orbit correction. The co-record is where we combine those two images in just one image. And with this, we proceed to do the interferogram formation. And this mathematically is an artificial operation. And after that, we do several complementary processes. I have to remind you that it is 10 minutes. Okay. Then, this methodology can be found in any of the papers. What we have done is to develop a geoprocessing model allowing us to do an interferogram in a much more automated and quicker way. And that's available for downloading. And the time it takes us to do an interferogram is 2 minutes. And is the time we use, only what we use for a periodical monitoring of our 23 volcanoes. As a result, as an event, some outstanding event or some examples, illustrative examples where we have detected deformations with sentinels in volcanic environments. For the earthquake of October 20, 2014, that's an earthquake in the region of Ilcontera in Ecuador, close to the Cerro Negro volcano. You can see here, this is the earthquake, the seismic event, we make reference to it. The 5.9 that was presented in this volcanic context. This is an histogram where we can represent from the period of November 1st, 2013 until November 13, 2015. It happens here. The volcano was showing some increase with some energetic contribution before the event. And then we have the seismic event very close to the volcanic issue here, 34 kilometers to the volcanic building. It generated an increase in the activity of the volcano, registering from 2,000 events per day until around 8,000 events per day. Then the seismic event occurred in the zone. With these interferograms, we have this pattern in the rolled interferogram, and then we have the unrolled interferogram. The quantification of the displacement showed us that we have a subsidence in the order of 7.5 centimeters and uplifting of the surface reaching 23 centimeters. These can be compared if they're coherent with other work from other authors showing images through commercial software. One more example we have here where we have detected deformation with EVENTO is the Sotará volcano. In this image, we see an interferogram for the period of October 2019 and January 2020. Basically, we are showing the volcano here, and the image tells you the difference when there is a deformation in volcano and when there is not. This is a volcanic compound called as Puraste volcano. That's a volcanic chain. You can see that basically there's no deformation here. And at the south, to the south here, we have another volcano called as Sotará volcano, where we can see a pattern where we have a displacement on the order of 4 centimeters. Then that led us to do a methodology, a specialized methodology with the work of radar cosas par, which is working with time series. So we replicate the periods. The periods was 2017, 2018. The images descending and ascending shows another period, 2019, 28, ascending and descending. Here, what we have here is the time series. The red points make reference to the time series obtained within SAR, and the points in black make reference to the GPS stations we used to have located in that volcanic building. Let's remember that there are coherent movements, and this here we can see that the pink color highlighted the 2 periods where deformations are detected. We can see that the first period is a slow deformation, and the second period we have a bigger and deformation occurring in a shorter period of time. And here we have the time series, the GPS stations. We have when monitoring the volcanic building, where you can see the deformation process. And what we do with this data? Once we have identified this deformation, what we do is to proceed to the modeling. And when we do the modeling, we try to quantify the parameters from where is the source originating the deformation, what's the location, the depth, the volume, that might be the exit volume for the volcano. In this case, for the first period, in this modeling, this period illustration, you can see that the model sources with GPS here within STAR are on the volcanic building. And for the second period, we have more GPS station, and the solution of the vectors was much better. Basically, those two sources are coherent, and it shows that the deformation source is above the volcanic building, an intrusion order of 3 million cubic meters to a depth of 4 kilometers under the top of the volcano. Conclusions or recommendations: we know that doing an interferogram in an ordinary way is a process taking time, and the permanence of one active user to execute each phase of the processing flow. The geoprocessing model we present here allows us to reduce those times of execution, and at the same time that all parametrization is included, and in that way mistakes generated by human factor are decreased. The magnitude for obtained results are coherent with other studies reported by other authors for the same stone of studies. This is an important point for Copernicus and all the work, because that's the point, the fundamental point for developing countries. We can access to this data freely. We can monitor activities due to volcanic activity. In this case, the volcano is an activity does not reach big heights. We have that the volcano is almost covered by more vegetation, but we can see the deformation with certain clarity. The coherence band resulting from the interferometric process can be used for the identification of certain coverage, such as ice, water, desertic area, among others. It's like studies we can conduct by using only coherence, depend on implementing other insert techniques such as VA, CITA, APS, to generate time series and explore more this in the technique of the volcanic monitoring. exploring applications of different missions observation of the Earth conducted by ESA Copernicus, such as Sentinel-1, Sentinel-2, Sentinel-3, Sentinel-4, Sentinel-5, since they are free data focus on a specific aspect of the Earth's observation in the scope of volcanic activity. It's pretty important because it monitors parameters of the descalcification such as CO2. So is to use all these technologies we can have here. And thank you very much. Thank you very much, Jorge, for the questions at the end. So let's go now to the presentation of Paula Olea. Paula is from the National Service of Geology and Mining, and she will refer to landslides. And from INSAR with Sentinel-1 using the Cernagiomin study case. Paula, the floor is yours. And keep in mind it is 10 minutes.
No tengo la capacidad de compartir todavía.
I cannot share screen yet. Just 1 second, please. So Florencia is going to give us a hand with that.
Adelante.
Ya. Bueno, el tema que
Perfect then. So I will talk about landslide and the usage of the insert with Sentinel-1 and the application used in Yerba Loca study, landslides in the year 2018. This presentation is structured in study, area study, the images used in radar and landslides, theories and relevant concept, analysis of the formation and landslide, methodological analysis, and some final considerations. The study case, it is in the metropolitan area, Mapocho Valley. There is a Yerba Loca stream that goes to San Francisco that finally gets into Mapocho River. The landslide area, it is at an elevation of 3,400 meters with no vegetation and with a high content of snow in wintertime. This landslide was seen, first of all, by Scientific Center of Valdivia, and they reported it to the civil protection system of the occurrence of the landslide. And the protection system, civil protection system, thought it was pertinent to do some analysis because there could be a bigger landslides affecting some populations in the nearby areas, high areas of the Mapocho River. So Senagiomin did plenty of studies, and it includes the analysis with PlanetScope images where they can see that the event had two parts. First one between the 6th and 15th of August 2018, the first landslide, and then later there was a second one on the 20th and the 23rd of the same month. So that could determine that it had a estimated volume of almost 3 million square meters. The trigger could not be identified, but there are some approximations, and it was said that possibly it could have been because of precipitation, rainwater, because a couple of weeks before, the biggest precipitation of the year occurred in this sector. The geological context. Titles are a little bit high. Can you see them? Yes, we can. So the geological context, it is found in the Parillones Formation Zone, which are volcanic rocks mainly, with highly steep valleys with a huge amount of cones and colluvial and some other elements which are related to some gravitational elements which are quite important in the context of the geomorphological context. We can see that the slopes and rocky slopes are also there, and some fluvial elements and some alluvial fans as well. There are some pictures, so we can see the landslides over there. We can see that it has at least two big marks where it moved, the deposit moved, the landslide occurred. And nearby there are some other zones of deformation and also some deposits of rock glaciers have been observed with some cryogenic nearby the deposit as well. the use of landslides or the radar images for the landslides. I'm going to synthesize this over here. One of the main elements that is being done, it is analysis with this automatic classification of the formation zones, as Udo just mentioned. It is on fashion to do these classifications in an automatic fashion in order to improve and complement the catasters of landslides, especially in places with a difficult access or where the satellite images, optical ones, do not allow to see or visualize the elements. In zones where there's high vegetation, it is hard to identify landslides because there is vegetation and then later it disappears, such as in the case of Santa Lucia. But in some other places where there's no vegetation, such as the Chilean Cordillera Mountains, it is hard to identify it because the geological characteristics and features of the materials, all the chemical characteristics are quite similar. So therefore, classifications from images, optical images, might be much more difficult. So determining the zones where there is a movement or where there are possible movements helps us a lot in order to improve the cadastre, which we already have. In this case, we're showing how these inventories of landslides are complemented, and they also contribute to the susceptibility maps, and they also contribute and support the generation of risk maps, which is quite on fashion because we have Sinopress, which is a new system that replaces all of the structure led by ONEMI, where it is necessary to do many risk maps with different variables, geological variables, which are important, such as the landslides. So this, or using this radar images, complements this analysis, and it improves it, identifying zones which were not so evident in the past. We can see in the graph down there the difference in movement between a zone which has a movement and another stable zone. As I said before, it helps a lot for the susceptibility maps. In the first figure, we have a susceptibility map where variables were crossed, such as height, altitude, steepness, type of geology, and some other variables. And then later, when being complemented with the B image, which is the one for LINSAR, the map could be improved, where some zones appeared, where in the susceptibility map did not appear at a plain eye. So in image B, you can see the difference between a susceptibility of A and C. We can see that clearly we have these other zones which should be hazardous or dangerous, and therefore we should monitor them. We should be concerned about them. It also helps us to characterize in a better way how a landslide is behaving and to characterize it in its phases in order to have a better response against phenomena which may affect human beings. A little bit of theory, I'm going to go through it quite swiftly about radar because you all know it, right? You talked about it, but I want to concentrate on this image, which compares how radar images are seen. A and B on the left, we can see how ascending and descending image looks like. What we can see in comparison with the ones on the right, it is the distortion having there in the lake. Second place, we can see the area of illumination, where the C image, for instance, the face looking to the east, it is much wider than the one looking to the other side. And on the contrary, the B image, we can see that the one on the east, it is much wider. So in order to work with interferometry, the side which is illuminated presents a better characterization because it has a better reflection or a better reflection of the signals which the satellite is emitting. Also, we also talked about how this interferogram, how it is built. And I just want to highlight that the traditional language talked about master and slave. And there's a new trend to decolonize language. And we use referent and secondary as an option, or some other terms that have been used in order to change the language, right? In order to understand the interferogram, we talked about the difference of phases and how each stage or each value of separation between this phase differentiation gives us a color. So the farther away it is, we start with light blue, goes to purple, pink, yellow, and then later green. So there we can see graphically this difference of phases, so we can conceptualize it much better. What I'm showing right now talks about INSAR, where we see an analysis with multiple pairs of interferograms in order to determine the temporal series of displacement or deformation of a certain place, interconnecting it, all of the different images in accordance to their dates and their phases they are at. The methodology is PSI, which talks about the permanent dispersers, and the dispersers, which are obtained just as it was mentioned before, are the places where the soil it is without any construction, with hard constructions where there's no vegetation or snow or coverage changing all over or through the time. So vegetation, it is a bad companion for this method, same as the presence or absence or snow. And water, it is not good either. So the zones, the cordillera or the mountain area of here in Chile, it is a great place because there is no vegetation, so there's no other elements, but this alternance of snow, it also affects the results. And we need to apply some strategies in order to compare summers, between summers, and we need to play a little bit to adjust the data. Deformation analysis of the landslide over here. So here we have a macro image of an interferogram where we can see that we are in the northern part. There is a mining zone nearby the metropolitan region. We have the glaciers towards the north of Hierba Loca. La Paloma Glacier is over there. We can also see the landslide area. If we see an image, an interferogram, usually there are some atmospheric elements or some other effects which are affecting our images. So therefore, when interpreting, we need to have plenty of knowledge of what elements are real and which are just the effect of the method itself, not to make mistakes. So sometimes we need to analyze it from different viewpoints. On the one hand, from the methodology itself and the physical conceptions which the method has, and also we need to have a knowledge of the study area. We need to know that there is some mine site, some glaciers as well. And we need to know, and we need to incorporate all of distributions in order to do a proper and more robust interpretation. This image, macro image, I like it because if I ask you showing this interferogram, and if I had not highlighted these areas, if you could you recognize the next landslides to occur, which with the zone which could be affected with the landslides? Possibly, no one would be able to say that, where the next landslide is going to occur. And that is a question that it is always quite interesting, because people are asking, is this method helping the prediction of the next landslide and where it's going to occur? And that's a question which is quite difficult to answer. Beyond, there are methods, identification, which are automatic, but knowing when and where it is going to occur, those are questions which we still cannot answer, and we need to work really hard to answer them properly. I'm going to zoom up the landslide area so we can see that in detail, a couple of interferograms. Here we can see the landslide. Paula, you're out of time. So in general terms, if we analyze this area, we can see that there were no dots, points within the landslide, but there was a zone in the northern part which had a high level of deformation, near 200 millimeters in these 4 years, which had been analyzed 5 years, 4 years and a half. And that really concerned us, and we could also observe an acceleration in the last period, which we analyzed. And that ratified the hypothesis that geologists had about this failure fault zone was still going to the northern part of the landslide. The methodological analysis, in order to compare the different precipitations of the sector, it showed us that there was a station upstream and downstream. On the one hand, we compared the correlation between the precipitation in the upstream zone in Piedra Carvajal, where there was no correlation, and then later it was compared with the precipitation in the downstream station, where there was a correlation which was quite high with the weather deformation. Talking about temperature, there was no correlation. And talking about the surface of snow from muddies, there was no correlation either. And with temperature, there was no correlation. So that's basically, this is an interesting methodology to be considered, and it's complementary to products that CERN is creating in terms of susceptibility maps and the landslide catalogs. And also, it is important to include or consider that it contributed a lot within the analysis of the landslide. And finally, as I said before, it is necessary to have multiple viewpoints in order to have a good analysis. Thank you very much, Paula. We're going to continue with the next panelist, which is Francisco Delgado. Francisco, please, can you share your screen? Francisco, he is a professor from mathematics. He's going to present INSAR in tectonic.
Hola, buenas tardes, Juan Carlos. ¿Se escucha?
Juan Carlos, good afternoon. Can you see my presentation?
Ya, perfecto. Entonces voy a empezar.
Perfect. So I'm going to start. So this INSAR has been a technique that has been used for the last 30 years for earthquakes, and different from what we're used to. When observing a seismograph, what we measure, it is what this geologist is measuring, which is the coast movement because of the tectonic plates when there is an earthquake, and that measurement of movement can be done with accuracy of a couple of centimeters for the case of an earthquake. So as I mentioned, this method, the theory of this method exists for the last 50 years, or maybe a little more. But the first application in active tectonic appeared in Nature magazine 30 years ago by the CNS agency from France. I will not go into details on how the method works because it's been mentioned before, but we're going to use the different phases of electromagnetic waves emitted from satellites which fly at a height of 700, 800 kilometers above the Earth's surface.
Mapas de colores que uno
And in
ve.
these colored maps, you can see here the interference. Depending on the type of satellite, each of these equals to a change of distance in the wave, and that depending on the satellite might be any of these three numbers. In the scientific articles on earthquakes, you can see two types of figures. On the left, we have one which is an volt interferogram, where each of the phases cycles you can see with these colored central areas that is difficult to interpret, but on the right we can see an interferogram and an roll interferogram, which is easier to analyze for any person that's not a specialist in the method. The difference from the rolled method, D has been converted into centimeters units. Then a technical characteristic of emissions of INSTAR that is worth mentioning is for by 2015 called for street map mode data. They might be very small, well, not big enough for the study of earthquake. And due to, thanks to the Sentinel missions with toxin and cancer with images weighing a lot of gigas, we can have a global coverage, because precisely what these methods do, we can see these satellites, we can see in the imitation of the European agency, the radar are to do this sweeping, and what this allows is to reduce the time, and today, as Oriol said, in Europe, by using the two satellites of the Sentinel mission, you can do a revisit of the same points every 6 days. The difference with the missions 20 years ago is enormous, because sometimes we have to wait for months at that time to obtain a deformation map of an event obtained by INSAR. And today, in best of the cases, we can have an interferogram that we are lacking 1 day after the event. And here there's an article, if you want to read it, if you want to see, this earthquake observation with INSAR. Then, what is what we're going to study when it comes to earthquake? First, we're going to understand the process of formation, where earthquakes are produced by cyclic mechanisms, where the faults are blocked and they release energy. And this conceptual framework, the subduction zone, where a plate is subdued under a continental plate, there's a blocking due to the properties of this fault, and that produces an uplifting before an earthquake. An interseismic uplifting that can be measured with INSAR is difficult. I can see this uplifting, which is equivalent to do a thesis work, but we can see the ecosystemic emergency when the plane of faults that produces obsidian signal and uplifting signal that depends the exact pattern at the places in front of the area of interest in front of the coast. That can be standardly measured with interferometry of radar. Then what differences is working INSAR versus seismology? This table shows a set of parameters that can be studied when it comes to earthquake. With the different symbology with INSAR, we can know what the earthquake is. We can determine the magnitude, and particularly the MW magnitude and the fault, and the INSAR allows us to see the fine infinite, and that cannot be done if we work with a teleseismic way, because they are reached from a big distance. But in INSAR, since we work with a model where we just measure the static displacement from the fault plan, we don't have time reference, that we cannot measure any dynamic data, time data in an earthquake, such as the seismic function. In INSAR, there's no distinction of close or of far distinction, no, the hypocenter, only the, and then the MW obtained from INSAR usually is bigger than the MW obtained from the seismology, because INSAR always includes some deformation after the earthquake, and in general, the rule depends on the depth of the event and the zone of study that we're going to study. Only those higher of 5 magnitude, lower can be studied, but you need to be lucky, and the data, the conditions of the data are useful for the method rather than a global monitoring condition. And this is just to show you that INSAR has been used to study a series of earthquakes for more than 20 years, since the Antofagasta earthquake in 1995. And the rest of the talk, I will refer to what the Chiloé earthquake in 2017 took place. Then this event occurred in the southeast corner in the Chiloé island, in a zone with very few instrumentation, and we can see in these lines are the dimensions of the rupture areas of the seismological contact with the Nazca and South American plate. This event was the first one occurring after the 1960 earthquake, which is the biggest instrumentally recorded. We can see here that this is a zone with a little seismic activity, particularly regarding to what happened to the north, which is the Maule earthquake. And we can see what happened after the 2016. It was a big earthquake. It was not a mega earthquake, since it just affected a relatively small area, 50 square kilometers, unlike the rupture zone of 1,000 kilometers in 1960. And then it didn't cause big damage, There was a tsunami there, but it was a relatively small tsunami, just some centimeters, having waves. So it was like unnoticed. So we can see here a compilation of a sentinel ascending interferogram, and then what descending, the black line shows the direction of the satellite. These are from Sentinel, these are from Allo 2, another from the Japanese agency. And the advantages and disadvantages are the following. The band C of Sentinel has a relatively low coherence. We have some difference in measurements that cannot be observed with a lot of those data. The problem here is that lost data has a temporary resolution very low today, 42 days, and they require special corrections to the manage ionospheric defects from the air band they are implemented in the processing software. This transition you can see in the zones of uplifting and subsidence are a hinge zone, and they say that the rupture, the deepest displacement zone of the seismogenic contact, reaches a depth of 50 kilometers, the one I'm showing here. And some repeated repetitions within some, you could not study here, only the other one. So in this study, we conducted with some geophysics colleagues, accelerographs, teleseismic seismogram, static GPS, INSAR, and micrograms or tidograms. We can see here in the image where we generated an initial modeling of displacement to see how much of this data can solve and the joint inversion. What is the result of the joint investment in this synthetic model allow us to recover the closest model to the original distribution of the check care work data. Then the combination of INSAR with our data allows us for a model of relatively resolution, but relatively high, and we can see the result investment, displacement of 3 meters with an displacement angle of 90 degrees. That means investment, and we have a seismic magnitude of the 7.6 according to the estimations. Here we can see seismogram, the different components of the accelegrams. All of them are modeled, pretty well modeled by the displacement model I showed you in the previous image. And here we see the same in interferograms, ascending sentinels, and synthetic interferograms modeling, well, I would say in general, and data and residual ones. And like the interferogram, there's a difference between the interferogram and the preset movement predicted by the synthetic interferograms. In general, it's difficult to model seismologic data as well as INSAR data because they are sensitive to different components of frequency on the process of rupture caused by earthquake. But in general, in this study, we can see that we can do it pretty well. So I'm finishing here, so I don't want to expand anymore. My conclusions of this presentation is that INSAR is a standard tool in the study of the seismic cycle of active faults, and that's partly due to the global availability of Sentinel-1 data, as been mentioned before. The method, despite it being much more used in arid zone, it also works in zones with plenty of vegetation. It has some problems, though. The analysis sometimes must be manual, and no automated processing chains can be used, but it allows us to study difficult zones from the methodological point of view, such as Alaska, Indonesia, and the Patagonia. And from the scientific point of view, this earthquake, the Chiloé earthquake, shows the displaced 3 meters with a displacement of 3 meters between the contact zone between the Nazca and South American plates. And this joint investment, and unlike other prior studies, allows to conclude that this earthquake didn't release accumulated energy before 1960. And the suggestions of these studies, those that were proposed that they were released energy before 1960, due to the non-use of all the set of broad seismic or seismic activity data. Thank you very much. Thank you very much, Francisco, for your work. We are going to go now for the questions. We have 3 questions here in the panel. The first question is by Mr. Donoso, Ricardo Donoso. The question is, there is any possibility to facilitate any document on the methodology used to conduct the registry of these landslides.
Eso yo me imagino que es para Paula, ¿no?
I suppose
And
this is
that
for
question should be for Paula, right?
Paula.
So, Paula? Are you there?
Parece que ya no. Voy a pasar a la
It seems
siguiente
we
persona.
lost Paula.
Eh,
Let's go with the next question.
Hay una otra pregunta.
There's another question for the panel
Sobre cuál es el software que se
about
utiliza
which is the
para
software which is being used for doing the INSAR.
¿Puedo responder yo? Sí, empezamos. Ya.
May I answer?
Hay varios programas
There are many different programs.
desde un punto de vista científico.
From a scientific viewpoint, the
Utilizados son el
most used ones are eyes from NASA and MHCSR from the California San Diego University. Both are for free. They work in Linux. They are not easy to use. They are quite cryptical, as Oriol just mentioned. The tools of the radar tool and the radar, while it is cryptical, it's not intuitive for people from coming from other disciplines. These programs are for free. They are done for being efficient, and they work quite well in order to create interferograms. There are some other softwares, commercial software such as Gamma, Swiss, also used in research, but it is $30,000 per license. There are different programs by different space agencies, the French one, and space, and some other tools as well. But the most important one is ICMTSAR, and both are for free. They can be downloaded for free from internet. There's another question. Is there any association or connection between the landslides? That question was for Paul, I'm sorry. So it seems there are no more questions. So Florencia?
No.
Not at all? Well then, so since we don't have any other questions, well, the emails of people are there, of the panelists are there, so you can send your questions to them through the mail. I want to thank you all. I want to thank the three participants, Paula, Jorge, and Francisco Delgado, for their presentations. And with this, we're closing this panel. And Carmen Gloria. But there's a question over there. Carlos Garcia is asking a question.
No.
Uno que habla sobre los ingenieros geomáticos tienen.
Oh, talking about the question is, do geomatic engineers, do you have a field in the seismological field? Yes. I believe with this earthquake, which is here in Chile, there has been, I believe the word is deformation, professional deformation, but the main feature, characteristic of earthquakes here in Chile the main tool to study them, it is seismology. But in some other places of the world, earthquakes produce effects, important effects, in the surface of the earth, with some superficial ruptures especially. So therefore, some other tools are used, such as LiDAR, topography, dams of high resolution, also observation of terrain, determining the geometry of the elements, surface. So earthquakes are geological events which can be understood using many different type of data, and therefore, people who have a training in geomatics can contribute a lot with this, the study of these elements. Seismology is just one tool in the case of Chile, because of reasons. I mean, it is not important to talk about in the reason. It is the main one, but it's not the only one. It's not the only tool that can be used for this. So yes, so these engineers have, of course, a field or a place to work in this field. Thank you, Francisco. There's one last question that we just got that says, and this is the last question that we have time for. Is there any methodology for calibration data of INSAR and GNSS? Maybe Orion can answer it. I can answer the question. Well, basically, what we do for modeling deformations in volcanic places, we convert the displacement of INSAR, which are in the direction of the separation of the satellite, loss displacement into vertical displacement. That is to say, from the angle of incidence of the radar image has an incidence angle, and therefore we need to do a mathematical equation converting that into a vertical displacement. And that is what we showed in one of the slides in order to do a correlation between the GPS data and completed modeling.
Gracias, Jorge.
Thank you, Jorge.
Ok, ahora sí, le vamos a
Well
dar,
done. So now we're going to give the floor to Carmen Gloria so we can continue.
Gracias, Juan Carlos.
Thank you, Juan Carlos.
Muchísimas gracias, Juan Carlos, y a Oriol
We'd like to thank Oriol and all of the panelists.
estas presentaciones
Thank you for
muy
these
interesantes.
interesting
Ahora
presentations.
vamos a tomar una
So now
pausa.
we're going to have a break, 5 minutes break, and then later we're going to return to the different rooms, the rooms you chose when you
Al volver,
enrolled into this workshop. After that, after these 5 minutes breaks, you are going to be in the breakout room that you chose. We have to say that if you wanted to change from room, you may do it. You get out of the room where you're at, and you can go to a different room you'd like to visit. So therefore now, I remind you that the main room, which is this one, it is the room that has simultaneous interpretation. The other rooms do not have interpretation because of platform restrictions, and this room will work with monitoring and prevention of. The second room will talk about room number 1, analysis of risk, analysis and management, and room 2, measurement and recovery of impact, recuperation from impact. So that is that. So we're going to be back in 5 more minutes. Thank you.
¿Aló?
Hola, no sé qué pasó.
No sé. No sé qué pasó, nos llevaron a
I don't really know what happened. So we're all here into this main room.
Hola.
Hola,
¿Hay alguien por aquí? Sí, ¿no?
¿sí? Estamos en la sala principal.
So this is the main room. Huh? We are here in the main room.
¿Aló?
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 Hola.
¿Aló? ¿Aló?
Hola, buenas.
Hola, Ariel.
¿Qué tal? ¿Cómo estamos?
Bien, damos el break, va a partir en unos minutitos. Ahí van
We're
a...
going to start in a couple of minutes. Matt is going to coordinate or lead this session, if I'm not wrong.
Good morning, everybody. It's actually my colleague, Lisa Hecker, who will be joining us, who's leading this session in the main room. Sorry, we seem to have, from my end, we seem to have some confusion around who has been assigned into which rooms. So I do apologize.
Yes, hi, sorry, thank you, Matt. I think I'm in the right room now. Sorry for the confusion. So can I just quickly confirm this is the room with the translations, and we'll be talking about monitoring and forecasting of geohazards and using Copernicus data for that. So everyone who'd rather speak about one of the other topics should try to switch the rooms now. And yeah, anyone who'd like to, the aim of this session is, sorry, is there a question? Okay, I think I'll just go on. So the aim of this session is to identify common interests in using Copernicus data for monitoring and forecasting of geohazards, and share experiences, maybe lessons learned or even problems. And then from that to see if we can derive some ideas for future projects or collaboration. So I don't know if anyone would like to make a start and introduce themselves and their work, or maybe ask a question. I'm hoping that people understand me and that the translation is working. Just seeing. Yeah, thank you, Matt.
Bueno, no sé cómo funciona esto, si se habla y ya está.
Maybe I just should speak. Is that the case? Do I just speak?
Yeah. Do you, I mean, you
Okay,
did, you did give a very nice.
Soy Uriel Monserrat, simplemente, pues
So, to start with, I just wanted to add a piece of information to the presentation that I have done related to projecting what we mentioned about the policies and distribution and the acquisition policy of Sentinel. This program, it is a program that is going to have continuity in the future. We have at least 15 or 20 years of warranty. And also we need to add an important piece of data, which is that we're planning, I'm not so sure if 2026 or 27, the European Space Agency is going to start a new session within the Copernicus, which is ROSE-L mission, which in the end, it wants to replicate Sentinel with L. That is to say, in the end, what we're going to have, it is a system, a star system in with L, which means with a bandwidth which is longer, and in the end, with a potentiality which is different, covering all of the globe, just like Sentinel does. I believe that it has been planned having the same print. So in the end, what we're going to have are two systems with bandwidth which are different, observing the same phenomenon. So this may contribute a lot from the monitoring viewpoint. It will also allow to solve many of the problems that we mentioned before at the time of monitoring volcanoes. Because of the snow, it's not going to be solved, but vegetation is going to be solved. And basically, just to mention that this is not something which is going to be finished soon. This has continuity. And it is important to have that in mind when planning monitoring systems for the future for different types of geohazards. A question. This mission is also, it will work with a ScanSAR top system or top. I'm not so sure about that because I don't remember that. But if you go to the Friends of the last year, there was a presentation quite long about the new missions of ESA. That was one of the first one. I guess that is available. And there was plenty of information about Rose L. Thank you.
Okay, thank you, Oriol. Are there any other questions about projects that have been presented today, or maybe also not necessarily? We spoke a lot about SAR data and radar data, but of course, monitoring and forecasting can also include optical data whenever that's appropriate. We heard reasons why SAR is more useful in many different cases than in others, but yeah, this discussion is not limited to just radar data, I'd say. So if you have any projects that you'd like to share with people in this room, or if you'd ask any more questions to any of the presenters that are still in this room, you could either come in here or maybe post your questions in the chat, whatever you prefer.
Como presentador, si alguien tiene alguna
As a presenter, if someone has a technical question on how to use the method for a certain problem or situation in a area which is not so well studied, I can also answer those questions. If someone's having an issue with that, or if someone's having a question with that, specific question about the methodology. Just to animate this, I would ask a question about the project European Ground Motion Service. Let's say, do you think it could be replicable here in Chile, in the Chilean context? Would you see some applications for it in Chile? Do you think it would be interesting to scale it to the whole Chilean territory, or do you think it is not needed from the territory management viewpoint? Once again, I'm going to answer as a person who's working with INSAR. I think there is a high interest, scientific and commercial interest, of having more products of monitoring, satellite monitoring from different types, deformation or changes on the surface or the topography of the country, both for mining applications, monitoring volcanic earthquakes, different vegetation coverage, and so on. The problem that I see on it, to have a monitoring system from inside of the whole territory, it is that the conditions, environmental conditions of the country are so different. In the northern part, which is a desert, where the method is easy to use, let's say easy, because there are some distortions. But in the southern part, there is serious coherence problems where up until today, I see we cannot really use these optimized tools of processing because the method, especially on volcanoes, cannot be used during 6 months per year, a year. So I see that there are some different applications which require different resolutions. For instance, the study of mining tailings requires persistent scatter, high resolution, the whole resolution. It is different from the small baseline analysis with interferograms of resolutions of 90 meters per pixel, which could be used for applications, tectonic or volcanic applications. So I wouldn't really know how to balance these two elements or resolutions at a national platform for the monitoring for the industrial, commercial sector versus the hazards. And at the same time, the difference of the coverage of vegetation over the country, where one solution, which is a unique solution, cannot be used for both applications in this case. The truth being said, the debate there in Europe was huge, because in Europe, if you go to a territory such as Norway, for instance, Norway, they have 6 months where everything is totally covered with snow, especially the northern part. So in the end, they decided to use the maximum resolution in the whole territory because of a question of, because in the end, in Europe, and maybe in Chile it would be the same, or it could be a little bit different. The main target, it was infrastructures and population. And here we don't have, I mean, here we have volcanoes, but we don't have as many as you. Earthquakes we also have, but not as many as you, not so often. And even though we have some important events, they are not something that really needs to be followed up. But I still believe that the problems that you're commenting, which are real, we need to think about them, sit at a table and talk about them. I'm pretty sure that we could get to a commitment between these two worlds, because in the end, engineering and geophysics and geology are diverse. They're so all of them so similar. The northern part is going to be easier, I'm sure about that, and the southern part different from Europe. What happens in Europe? But we should do it. On the technical viewpoint, I think we could get to a commitment, to a balance. What I see is that we need to do two processing chains, which are different. One with high resolutions, as the one you mentioned for infrastructure, and another one small baseline with interferograms, multi-looked interferograms for the central so part, concentrated in risk. That is what I'm thinking about.
Okay, thank you. I think Juan Carlos, did you have a question? Did you raise your hand, or did it?
Yes, in Spanish, right?
Yes, of course, yeah.
Okay. Sí, yo
Sí.
quería,
So I wanted to tell you, I understand that that is a problem in the analysis of the signal. There is a problem in the analysis of the signal, but it would be important to determine the coverage of snow during that period of time, especially in winter time in this zone, especially for those companies that are using water coming from snow melting, or also for watering. So an important application that up until now it is not being considered, it is determining the amount of snow that falls in wintertime that gives and transform into water because of the melting. We should determine what volume of water could we have at certain periods in winter, or summer or spring. That is true. With the coherence products, you can see clearly how the coherence lowers seasonally due to the snow falling. And the amplitude images, you can also see how snow disappears or falls through time. How to convert that, which is a change map, into a number, a volume that is a totally different beast, but it could be done. I would add about this topic that this situation of snow, it is a topic that requires research. It is actively being researched with radar, because radar has a potentiality with one of the parameters, which is the most important one, which is snow water equivalent, the amount of water in the snow, which is independent from, let's say, we can measure this independently from the density, which is a really hard parameter, and the depth. So just because technically it is possible to do that, then it's been studied for quite a long time how to obtain that parameter. The problem that we have found when we use radar, it is water. Snow, dry snow, has some properties, and once it gets wet because it rains, or because the temperature rises and once again goes down, then we lose all of the information which can be extracted about the snow. So, we have been using, or we're trying to use the phase with different bandwidths, because the delay of this phase, it is shown in the snow water equivalent. And the main problem that we have, it is that snow changes its condition at the basin, not valleys, and it could change so much, and that makes it really hard for extracting that precious number that everyone wants to obtain. So what it is being done, there are some works with SAR, but terrestrial SAR with different frequencies, multi-frequencies, in order to try to get that information at a valley. So from a stream, because maybe there's a dam. So they try to make an estimation. So it is always experimental. Getting the magical number, it is still a dream. And many people, of course, are going to pursuing. I'm talking about with SAR, satellite SAR, right? I suppose you were talking about that parameter, right? That's right. Or amplitude can also be, there are some models that correlate the softening of the bandwidth with snow water equivalent, but there are many parameters in order to control or obtain a robust estimation at a basin level, or let's say wide zones.
Okay, thank you very much. We have a couple more questions in the chat, and one is whether machine learning has been used with that type of SAR data. And if so, how difficult or what the difficulties are around that? Could anyone say anything about that? I'm assuming that refers to interferometric data, but maybe it's just SAR in general. Yeah, Erling, do you want to come in on the machine learning aspect?
Sí,
Thank
exactamente.
you.
Bueno, sobre machine learning.
Yes, about machine learning, I have used machine learning. There are many opportunities and applications that have to do with INSAR. One of them has to do with a line, which is really important in climate change, in glaciers and plagues, snow, ice plagues. That is detected with interferograms, and the interferograms, there we can clearly see that line. So that line, we should draw it by hand. We have plenty of interferograms. Drawing it by hand, it is really difficult because of time. So what we want is that through machine learning, we can activate these line creations automatically. So it's been feasible to do. Something else with machine learning related with it, but not with INSAR, it is finding the front of the glaciers and that type of things. So there is machine learning for work, to be applied with INSAR, which is compatible with INSAR. How can I raise my hand? That's my question here in the simple form. There's a button down there in the toolbar that says reactions, and it says raise your hand.
Perfect, thank you. Oriol,
Yes.
yeah?
Sí, quería preguntar al último. Sí,
I wanted to ask the person with that made the last presentation. Could you please send me the reference? I was really interested in the article, because it is something we're working on. And my question is, how can you make a difference between the type of phenomena that you are mapping? Because in the end, it is a classical application of artificial intelligence. You can see it outside, and artificial intelligence, of course, make it more automatic, right? Something which, of course, it takes a long time. So the question is, once you have identified all of the ways, how do you classify the different shapes? How do you classify them as glaciers or any other type of phenomenon? Well, mainly, it all depends on the grounding line. I don't have anything here to show you, but maybe you can find something. I can share some of the papers that have to do with this limitation of the grounding line, which is done through interferometry. And this is something which is clearly identified. And usually when we do the input with CNN, in the network, the idea it is that you're going to have many variables which are going to help you to delete, some false positives. And that is fundamental with this type of technology, eliminating false positives, because the training of the computer, according to what it's learning, it may give you plenty of false positives. And in that case, the grounding line is going to go to zones where there's no water, but it is above, it has to be above rock. So that's one of the things that we need to do to make a difference. So what it's usually in the training, we have a set of databases where one database has to do with the image itself and the result of the insert itself. Another one has to do with the direction where the glacier is moving, which has to do, of course, with where you're going to find the line. And there are many other databases that you can also insert for that to happen. And the same happens when you want to draw the front of the glaciers automatically. You have to identify which is the side where you have water and when it is where there's ice. And there are many other things which technologically need to be given. But all of that set of data, which are used for the training, have to be given beforehand. And that's the key of all of these processes. Does it answer the question? Absolutely. Yes, thank you very much.
Cool, thank you. We have two more questions in the chat. I think one from Matt, which picks up the question around snow and water equivalence. So I'll take that one first. And he asked that in terms of snow water equivalent, is the interest in these calculations focused in terms of water provision or hydrological risks or both? Would anyone like to answer that question? No?
Yo al menos cuando nosotros hemos estado trabajando.
Well, we have been working on this. We'll continue to work on this. We talk more on water supply. In our case, I don't know if that's important in terms of hydrological risks. One more thing that I can add is about the equivalence. When you generate an interferogram to later get a field modeling on glaciers to see how much the elevation and the volume of these changes, the amount of water contained in the upper part of the glacier, because it's important because the penetration of the start can tell you about a mistake. That's a factor to consider when you need to verify these changes in elevation and the amount of water you have, whether you have it or not. That's another extra data.
Okay, cool. Thank you. I hope that answered Matt's question, and we can move on to another one from Eric. And he asks, do you think it is technically feasible and economically viable to use Earth observation data to determine historical and forecasted wind and solar data that are relevant for offshore wind energy projects and solar PV projects? Because we know pretty well that renewable energy projects are important to combat climate change. Is that is that something anyone in the audience has considered or been working with or came across a case study or something? That doesn't seem to be the case. Yeah?
No sé, yo puedo hablar, pero no histórico.
Well, I can say, but pretty historical, I would say. Now, there's a new satellite called Aeolus, which is capable of, through microwave, to determine the direction and the speed of wind. And there's also some temporary or time data regarding the direction and speed of wind to generate some models on which the most important areas where these should be, where some wind stations should be placed. That's on my side, what I have seen.
Okay, thank you. It's looking like people are coming back. Is that true, Florencio?
Sí, la verdad es que
exactly, yes. That was pre-set to end this time, and since we started a little bit later, I didn't realize that the time was going to be shortened. So my apologies. Well, my apologies for all the mess. Of course, today we trusted the automatic settings of the room to improve the speed between moving from one room to another, what happened last time, but again, we faced it. So my apologies once more. We're gonna have to stay here, seeing what the problem is and how we can solve it for tomorrow. So it's unfortunate. I hope you have been able to talk in your groups and you have made some progress. And since Juan Carlos is the chair of all sessions, I'm going to hand it over to him so that finish, which is the room's report. Juan Carlos, just to clarify, Lisa Hecker, which is in the screen on the top part. She's in charge of what was talked about in the monitoring room. In room 1, which is the room of risk, was Roxana Trujillo, and I took charge. Also, because we wouldn't be able to move you to recovery and tracking rooms. So, well, the floor is yours, Juan Carlos. Thank you very much, Florencio. Well, I was in the presentations. I participated in them. So, do you think that we can go immediately to see what some of the observations have been in the main room? Lisa?
Yes, yeah, we did speak about monitoring and forecasting, and Oriel gave us a few more details about his work, and that is going to be continuing on an ongoing basis. And we did have some discussion about upscaling and the difficulties that come with that as well, particularly because of the variety of habitats in such a large area, if it was to be upscaled, for example, over all of Chile. And then we talked about machine learning applications a bit, and yeah, especially but the difficulties between water and snow in interferometric data. That was, I think, the main points that we covered in room 1.
Okay, thank you, Lisa. Ya. Entonces pasaríamos a la sala.
Then we'll go now to room 1 about risks and management. Thank you. Good afternoon. Well, we were in risk management, and what we talked about it there with the attendees were some points, very well-defined points. I like to summarize. And it's something that was mentioned, which is formation. And when I talk about information, I talk about the capability of training educators, teachers, and future managers of risk or decision makers within public policies, for example, in the processing of this type of data, because we have all seen today during the presentations that it's not a simple piece of data just for generating. This is why we still need to find the way to deliver and generate more knowledge for trainers as well, teaching, so that our new generations know that these tools exist, so they can integrate them in their labor points. Let's talk about interdisciplinary fields. It's probably the same. Is to talk about risk management. And the other thing is the approach into citizenship. It's been mentioned that in order to process and generate all these supplies which on today, it is necessary some type of knowledge, geophysics, mathematics, advanced knowledge. However, knowledge within the territory of the same citizenship might be accepted. The daily knowledge specialists do not have in their research place, for example, which is the computational part. So therefore, how to communicate and how to consider population as local people within a territory so they can support these dynamics of the environment, the existing ones. And finally, something that been well manifested, and I think that we'll see how to do this, which is training and practical workshops in the data use that has been mentioned by several people. When it comes to the, well, compared to the initial training, which is the student training, but professional training, professional workshops, considering that today we are working and we are hearing about these new technologies, they are being closer and closer, they are more accessible and there's more data, but we still need more teaching how to generate meaning and analysis. So we stay here as a Copernicus program with that work that may come in the future to generate that training and the data processing. So thank you very much. Thank you very much, Roxana. Florencio, please.
Para la sala de gestión post-event.
For post-event management room. Honestly, we were kind of slow, I suppose, because of the chaos in our room. I don't think that everyone wanted to be in our room. So once more, I apologize for that. But we had a brief conversation, fruitful conversation as well. There are some phenomena that might be not that spectacular, and however, they do affect infrastructure. For example, in the case of the Ministry of Public Works, when they have highways that sometimes they are ruptured and they suffer from displacements and changes, and they can reach 1 meter a year. And that basically means that hills where they are placed, they are moving, and they are moving because in Chile, in particular, throughout Latin America and all the fire belt, we have permanent earthquakes. We know that, we are accustomed to it. We sometimes do not even realize about it and we laugh, but they are acting on geology, and certainly they produce changes on the roads and other infrastructures that might be very critical as those. Then this work that in monitoring, that monitoring should include monitoring systems for that type of deformation. They are more constant deformation, less spectacular, that's the point there, and also less damaging from the human life point of view. But they do have consequences both in logistics and in costs. So there's an interesting topic because we have used interferometry and other type of tools when producing a service. Monitoring as a structure might be something that's still pending. Another subject that we dealt with here is how to access emergency services when there are events. And I mentioned the international charter allowing access to a set of satellite data from all, well, practically from all satellites in the world when there's an event, and during certain time, and it's activated by the official organs of the governments and the country, which is part of the agreement. And in Chile, it is my understanding, we're talking about the National Office of Emergency, or NEMI, through the Undersecretary of the Home Office. Now, apparently, some offices feel that may directly access these type of services, and probably what they can do is to access directly through MS, and obviously through Copernicus, we will always be willing to do so. But the charter is something that's hugely key and essential in those cases. We anyways take the observation on how there might be some more direct things with Copernicus. And finally, the regional maps update by combining the information from satellites and in situ data. This concerns by some regional offices, and we're going to take that as a future concern for possible projects. Thank you very much, Juan Carlos. I'd like to ask an open question to everyone. Since the idea is to build applications and collaboration networks, and from this point of view, each of the groups, of these three groups, how do you see we could have some type of network building where Copernicus Chile could support you directly when working with applications, so doing some management in the matters you particularly develop? So I open the floor. If you want to participate, you may raise your hand, then I will know who wants to speak. That's an open question for all the panel. Huh?
Tal vez para romper el hielo, Juan Carlos.
Maybe to break the ice. There's someone raising their hand. It's Jorge. He has raised his hand. Thank you. I think it is one of the important things is to strengthen this methodology, because for many people, for many institutions, what this technology is relatively new, and it can be seen as a methodology that is effective, but implies a software, as the speakers have said, sometimes it's kind of complex, complicated. It also implies having good condition machines for processing. It implies to have a big storage information. Each image weighs around 4 gigas. I think that this type of workshops are pretty useful, and we can see that they are very interdisciplinary. People working in volcanoes, earthquakes, slides. So it would be important to suggest or to propose type of association or network where we can conduct some workshops, but longer, like a methodology. Let's say we're going to do a next month and we will calculate an interferogram with an X software, and those people interested in that area can join us. For my part, I'd like to share that there's an application developed by the NASA, by the JPL, called P, which is an online application enabling generation of interferogram for free without the need to use computational resources, not robust resources. So you can enter internet, select a couple of images, master and slave, and they send us to your emails the program, the interferogram. We have made some comparisons. The results processed with Snap and ICE, and the results are pretty good. Then maybe in terms of analysis or risk management, you do not have the time to process. You need to be generating information continually. So using this type of tool seems to be something important. I'll write the link in the chat. If you don't know it, you can see that link. Thank you very much. Thank you very much, Jorge. Lorenzo, you wanted to say anything? Yes, what I wanted to say is just simply remind you that we keep about the thing about network building, and we do this quarterly, every 15 days. So you're all kindly invited from Latin America and Europe, of course, and it's done on Mondays. Yesterday should have been the day, but due to this event, we're going to do this. But in 2 more weeks, which is December 13th, there will be another seminar. So those who are interested in keeping in the information in those seminars, please email us, and then you can be registered in the distribution list, and you will get an email every 2 weeks. You won't be bothered that much. And we also have a Twitter account. I will also write it in the chat. That's always updated, and we say what we are doing. It's a very good way to generate networks. People who normally connect to the presentations, it's more specialized, people are meeting size smaller, but we talked a lot more. Then we deal with all the subjects of using satellites, from interferometry, going through optical to altimetry and so on. All technologies available in the different satellites, not only from Copernicus, fundamentally from Copernicus, but not only from them, so that we can have a broader perspective. That's a good start point. There might be other things. We had a hackathon some time ago, and we gathered 60 teams to develop applications. And how Roxanne was saying, just like what she was saying, it was emphasized by Jorge, we need to look for the way to generate more conversations in some type of seminar or some more intensive things. As a matter of fact, Copernicus does a lot of that. Certainly, in many cases, it's in English, but there are several cases where we have content in Spanish. So if you enrolled in that list, I will try to replicate those experiences by emailing them to you so that you don't miss them when they are available. Jaime? I just wanted to say that included in the chat emails, Florencio and mine, to add you in the list. I also included the Copernicus Reference Center webpage where you can see seminars are hosted there. And I also included the link of the Copernicus repository we keep locally. Once the images by Copernicus will be available there, so you can download them. Uriel, you have raised your hand. Yes, I just wanted to add regarding your question about possible projects and what my contribution could be, and based on Carmen's comment, the need for training, I like to say that, in my opinion, that would be a strength task by Copernicus, which is improving training. And to say something, in my opinion, training, it's a void we need to see, gap we need to fill here in Europe, in Spain, from research and also from industrial areas. It doesn't mean that final users know how to process, but end users know the technique and also believe in the technique. Because the big gap we have here, in my opinion, is that there is lack of knowledge. Okay, we have a theolite, people get confused and people believe in interferometry. Satellites are optical, very not much. But what happens if there is a complete lack of knowledge in the technique and lack of trust? That's something that needs to be improved. And it needs to be improved firstly with the training on the final of the end users, and then finally with the work to fill in the gaps. The results we expect produced, experts in INSAR, and the maps used, people who make the decisions. Then we have a long trajectory to go through, which is products, maps, to be geared towards the needs of each of the various scales of people who bump into this decision-making chain, people with some priorities and mechanisms. We talk about civil engineering in construction projects that some other, they have different needs, and INSAR might be of help. But currently, the product we have, the main result is pretty complex to provide you with real help. And I think that we need to give education to users and also to work on communications in the improvement of what we provide you with. And in that sense, I think that our role in Chile might be down. partially that one, providing this, offering that, which is something we need, and it's missed a lot generally in the world. I can just tell you the amount of engineers who do not believe it. See, just that. That's incredible, incredible. Thank you, Oriol.
Carlos, no solo quería, no sé si puedo decir una cosita.
I just want to say something here. I believe that Oriel's point is pretty good. Instar, before and after Sentinel has changed a lot. It used to be a very expensive technique. I remember that I talked to people from Avers how much was a radar image, and 1,500 euros was for per each image, something very difficult to have access to. And somehow Sentinel democratized the use of Instar. But on the other hand, we need to disseminate knowledge, and Instar is relatively new. I'm learning from it, and it has complexities. But fortunately, there are a lot of people working on it now, eager to teach. I'm a person open to Will Francisco Delgados from the University of Chile, implementing an interferometry training course within the faculty. Then I believe opportunities start there to try to aim to interaction and cooperation. There's plenty of projects in interferometry for different aspects. That's a pretty good moment to build networks, to talk, and among each other try to learn and harnessing what we are doing. Does anyone else like to comment? I think there's no more comments. I'd just like to thank everyone for participating in this first day. I think that we made it, and we have achieved some conclusions, such as there's still plenty of things to do related to geological disasters, for example, or the geological hazards or risks. So I would like to conclude by inviting you for Wednesday, December the 1st, for hydrogeological risks session, chaired by Jaime Ortega. That's everything right now. Once more, I thank you, and I'd like to hand it over to Florencio. Carmen Gloria, Carmen Gloria. Thank you very much. That's okay. I'm gonna give it over to someone else. Once more, I apologize for the problem with technology. We solved it, and it was interesting. I think that Juan Carlos has already invited you for tomorrow, and now Florencio will close. And don't forget to join us tomorrow. Thank you very much, Carmen Gloria, Juan Carlos, to the speakers. Despite the problem with the rooms, not many people left, so thank you very much for your patience. We took several notes. We will analyze them, and we'll see how we can make them into useful information so that we can still promote the use of Copernicus images. We believe it's a great opportunity, as had been mentioned by many. You are kindly invited for tomorrow. I repeat what Juan Carlos has said. Tomorrow at 10 a.m. Chile's time, 13 Universal Time, we'll have the session of hydrometeorological risk. We'll say how water can make us sink and some of the damages. All right, so thank you very much to everyone, and see you tomorrow. Bye-bye. Thank you very much.
Gracias.
Thank you.